Hi everyone, and thank you for attending this talk. My name is Leslie and Daniel, and I will talk about the work we did with Sébastien Bardin and Tamara Resk on efficient symbolic verification to detect Spectre attacks. Spectre attacks are microarchitectural attacks that were made public in 2018. They exploit speculation mechanisms that are implemented in almost all processors to improve performance. Basically, an attacker can force a misspeculation so that the processor executes the wrong sequence of instruction. These incorrect executions, called transient executions, are reverted at the architectural level, but changes to the microarchitectural state, for instance the cache, are not reverted. In the end, an attacker can use this mechanism to force a victim to encode secret data in the cache during transient execution, and later recover these secrets with cache attacks. There are several variants of Spectre, but in our work we restrict to Spectre-PHT and Spectre-STL. Spectre-PHT is the most famous variant, and it exploits conditional branches. Let's illustrate it with an example. So here, IDX is an attacker-controlled input. The program first ensures with a conditional branch that this index is in bound, and then performs a memory access into a public table and loads the value into a variable v. Finally, the variable is encoded into the cache by a function leak. So this program is secure because the conditional ensures that the index is in bound. However, in transient execution, the conditional branch is misspeculated, and the program performs an out-of-bound access that can possibly load secret data into the variable v, and then leak it to the cache where an attacker can recover it. The other variant we will talk about is Spectre-STL. It exploits the fact that loads can speculatively bypass prior stores. Let's again illustrate with an example. So in this program, a secret S is stored at an address A. Then it is overwritten with a public value P. Then there is a third store at an address B that is distinct from A. And finally, the program loads the value at address A and encodes it into the cache. Here, the program is safe because the data that is leaked is the public value P. In transient executions, the load can possibly bypass prior stores. So we have a first possible transient execution that bypasses the last store instruction, which is okay because A and B don't alias. However, we also have a second transient execution that bypasses the two last store instructions. And this one is wrong because now the value loaded into V and encoded to the cache is the secret S. And so we have a Spectre-STL vulnerability. And finally, there is a third execution where all the stores are bypassed. Okay, so now the question is, can we detect these attacks? Well, it's challenging because first, the semantics is not really intuitive. We have to represent new speculative behaviors that are not visible at the architectural level. And there are a lot of them. Especially for Spectre-STL, we have to represent all possible load and store interleavings. So even on very small programs where the regular semantics has only 14 paths, the speculative semantics produces 37 million paths, leading very quickly to path explosion. And finally, our analysis needs to hold at binary level. But we like challenges, so we decided to contribute to the verification tools against Spectre attacks. In particular, we verify a property called speculative constant time that guarantees the absence of timing attacks under a speculative semantics. And for this, we use a technique called Relational Symbolic execution, which is basically the adaptation of symbolic execution to information flow properties like speculative constant time. And so, the remaining challenge is to model Trojan behaviors while avoiding path explosion. So there are already some verification tools for Spectre. However, for Spectre-PHT, they either don't scale to real-world crypto on binaries, or they operate at LLVM level, and so they might miss speculative constant time violations. For Spectre-STL, there is only one tool, Pitchfork, but it doesn't scale even on small programs due to the path explosion I mentioned. So the tool we propose, Haunted, makes Spectre-PHT analysis scalable on real-world crypto at binary level, and for Spectre-STL, it is able to exhaustively analyze small programs and find bugs in larger code. So to sum up, we propose an optimization called Haunted Relational Symbolic Execution to detect Spectre violations. Its key idea is to represent both transient and regular behavior at the same time to limit path explosion. And we also give a formal proof that it is equivalent to an exploration strategy that would model transient path explicitly. We implement this technique in a tool called Haunted and perform experimental evaluation on real-world crypto. And we also compare against state-of-the-art tools, CliSpectre and Pitchfork. Finally, we report 2 Spectre-STL violations, first with the index masking countermeasure against Spectre-PHT, and second in the code introduced by compiler for position-independent code that we won't discuss in this talk, but that you can find in the paper. First, let's recall how symbolic execution works on a small example. So symbolic execution executes the program with symbolic input instead of concrete input, and it builds a formula called the path predicate to keep track of the current path. Here, it is denoted by. In our example, after the evaluation of the conditional branch C, symbolic execution forks into 2 paths. On the first path, it executes the function foo and adds the condition C to the path predicate. While on the second branch, it executes the function bar and adds the negation of C to the path predicate. Now, to model the speculative semantics, we have to add 2 extra transient paths. The first transient path executes the function foo but adds the negation of C to the path predicate. And the second transient path executes the function bar under the condition C. So these transient paths are executed until the maximum speculation depth is reached. And this is the exploration strategy that is introduced in CliSpectre. In the end, it forks the execution into 4 paths, and we just have to verify that no secret can leak on this path. Now, instead of forking into 4 paths, we show that it is possible to fork into only 2 speculative paths that encompass both the transient and the regular execution, and this can be done by just delaying the update of the path predicate until transient paths are invalidated, and this pairs 2 paths at conditionals. So now let's look at Spectre-STL. Remember the program that we introduced at the beginning, performing 2 stores at address A, 1 store at address B, and loads the value at address A into the variable v. So after the regular execution of this program, we have 1 path where the variable v has value p. Now, for Spectre-STL, we also need to represent 3 additional transient paths to represent all possible load and store interleavings. So this is the approach adopted in Pitchfork, but unfortunately it quickly leads to path explosion because we have to fork the execution like this after each load instruction. So first, we noted that most of these cases are redundant because load and store naturally commute when they do not alias. So we use a simplification called read-over-write to detect and prune these redundant cases. Finally, because it is still expensive to fork, we encode the remaining cases in a single path using symbolic if-then-else constructs. So basically, we introduce 3 Boolean variables that represent possible transient paths, and we use them to construct an expression that encodes all the possible value that the variable v can take. And finally, this transient path can be invalidated by setting the corresponding Boolean variable to false. And so in the end, we only have to explore a single path that encompasses all possible transient and regular executions. We implemented our technique in a tool called Haunted and evaluated it on a set of litmus tests, cryptographic primitives T and Dona, and finally on more complex primitives from Lipsodium and OpenSSL. So first, we measure the effectiveness of our tool. We showed that for Spectre-PHT, it can exhaustively explore real-world crypto, and for Spectre-STL, it can exhaustively explore small programs, but still finds vulnerability in larger code. Second, we evaluated how Haunted Relational Symbolic execution performs compared to the explicit exploration strategy. And finally, we compared against state-of-the-art tools, CliSpectre and Pitchfork. We showed that for Spectre-PHT, our tool is equivalent or better than these tools, and for Spectre-STL, it clearly outperforms them. So I won't go into the details in this talk, but you can check the paper if you're interested. So for the comparison of our Haunted optimization against the explicit strategy, we start with Spectre-PHT. So first, on our set of litmus tests, we see that Haunted prunes redundant paths and therefore is significantly faster and finds more bugs than the explicit strategy. On Lipsodium and OpenSSL, it achieves a much better coverage and has less timeouts. However, on T and Dona, both techniques are equivalent. So we conclude that, at worst, there is no overhead with Haunted Relational Symbolic execution, and at best, it is faster and achieves more coverage and has less timeouts. So for Spectre-STL, Haunted clearly outperforms the explicit exploration strategy, and in particular, it avoids path explosion and doing so achieves a better coverage, has less timeouts, and finds more bugs. Finally, using our tool, we discovered a weakness in index masking, which is a countermeasure against Spectre-PHT. So remember the program that we introduced at the beginning of this presentation, which is the typical conditional branch check vulnerable to Spectre-PHT. The index masking countermeasure strengthened the branch check with a branchless bound check by applying a mask to the index in order to constrain its range. However, with GCC 00, the masked index is stored in the memory before being loaded and used. And with Spectre-STL, the load can bypass the store that does the masking, allowing an out-of-bound read. We propose mitigations for this that we verified with our tool. So the first is to compile with optimizations enabled, but its effectiveness might depend on the compiler. And the second is to explicitly put the masked index in a register so the masking cannot be bypassed. To conclude, we presented an optimization called Haunted Relational Symbolic Execution to model regular and transient behaviors at the same time. It alleviates the cost of modeling speculative semantics and improves over state-of-the-art techniques. We implemented it in a tool called Haunted that we open-sourced on GitHub. And finally, using this tool, we found interesting violations of Spectre-STL. Thanks for listening.